Yeah. Eric? Everett?
dy over dx.
Yeah, let's talk about that. That happens to be this one right here. Let's talk about that. We do read that as, Everett said, dy divided by dx, or dy dx. Actually, we just say dy dx. The d in those, well, let me just tell you this. Most people at this part of the semester will say, do not think of that as a fraction. Think of it only as notation. And then later on we say, okay, let's break it apart. I mean, it really is a fraction of sorts. It is notation, yes, I agree, but it's much more than that. I want to try and explain that to you. We don't really get into that until someplace in Chapter 4, but I do want to get into that. So let's talk, first of all, what does this x represent? The input. Yeah, the input. Just like it, the x up here represents input. What does y represent? The output, okay, just like we would look for y anyplace else. We really call this the differential of y and the differential of x. There's a differential spelled down there someplace, okay? Differential y and differential x. In some ways, it is connected to, and it does refer back to the same thing as delta x and delta y. Okay. Now, there are some math professors who would disagree with me on this because, I don't know, they're thinking about it as, and of course, beyond Math 50, okay, maybe Math 100 or whatever. So those of you going on into math, pay attention to what I'm saying, but also keep in mind that later on, you really do think of that as a single unit, not as breaking it apart. But let me tell you why you can actually think of that as a fraction. Let's just look at that curve, and let's say that this is x, and over here we have x plus delta x. We call this delta x, the difference between the two inputs. And then if I have the point here on the curve, and let's say that point's up there, this down here, this is f of x, and this would be f of x plus delta x. And so we call this delta y. Okay, if I connect that with a secant, so if I connect that with a secant, that's supposed to be a nice straight line, which it's not, but you can imagine. Whoops, that really looks bad. But anyway, that's supposed to be a line through a secant line. So our delta x and delta y is describing what's happening along the secant line. Now I'm going to put something else on here. I'm going to try very carefully to draw a tangent line. Okay, a tangent line through this point x. When I draw a tangent line, the new point has a point on the tangent line up there. It's not the same thing as up here, right? There's a difference between those. And if I come over here and I draw this over here, this is the output corresponding to the output value corresponding to where the point is on the tangent. Now, between these 2 points, it's the same thing. Delta x, differential x, it's the same thing. I'm measuring a distance between my point x and another point on that line. However, this difference right here is not the same as this difference over here. We call this differential y. So it's still slope. It's still looking at the difference between the outputs between this point and another point, but it's along the tangent line. Just like delta y is looking at the difference along the secant line. Again, at this point in the semester, we're going to think of it as just a unit. We're not going to break it apart, but then later on, we do break it apart. We do talk about it differently. And so maybe this will resonate with that discussion later on. Okay, so it's the same thing, but it's along the tangent, not along the secant. Okay, so we've got the input is x and the output is y. There's another way that we can write that, and it looks like this. how do these two, how are they similar? Yeah, Eric? Yeah, we've got the x's, we got the inputs down here. And yeah, the y and the f of x both represent an output. So we're saying the same thing. Now, we're going to be using this a lot, especially when we get into our quotient rule and our chain rule and all those other shortcuts that we can use. And we're going to be doing things like this. We're going to be looking at writing things such as the derivative. And so that top D is we're going to read it as the derivative with respect to x, because x is now, in this example, it doesn't have to be x, but in this example is our input of, and maybe we have something like this, 3x squared plus 4x minus 2. Okay? So we're going to be using that notation a lot, and we are talking about input is still the same. Input is x, just like it is up here on the simple dy dx. The output is the same, only we're going to spell it out. We're going to write the expression for that. Okay, so kind of keep that in mind. Okay, so that's one of the notations. Now, there is another way that's similar to this. Does anyone know where we're going with this? What's another way of writing the notation for a derivative? Yeah. Yeah, y prime. Okay, so we're going to use that. We can use that too. And again, it's similar to f prime of x because f of x is the output expression or output symbol. Y is the output symbol. And so they're the same thing. Now the fourth one, or the fifth one, is a little different. I really don't know of any problems that use that notation, but I'm just going to let you see it also. It may be there, and I just don't use the problems in the lecture, and I don't choose the ones for homework. But it's just another way. Now the derivative with respect to x. Okay. Now let's go back to your inspires, because again, you can do this on your inspires. And I want you to know where. It's going to be in the symbols palette. So find the symbols palette. If you're on the touchpad, it's got a key of its own. If you're on the click pad, we're going to use control multiplication. And in the second row, this symbol right here is going to be the one we're going to use. Now there's others that we can use for other types of problems, but basically we're going to use this one right here. If you press enter, we have the template, and again, you have to put in the variable of differentiation. In other words, the input variable doesn't have to be x. There are problems that we don't use x for everything, but we can use x here, and then we put in the expression, whatever that expression happens to be. Let's see, the last thing we were looking at was x cubed. Plus 2, and you get 3x squared. Isn't that what we got on our work? 3x squared? Okay. So that's how you can use this to check your work as you go through it. Okay, so the symbolism, the notation we use, it's important to know that because we are going to be mixing it up a little bit. If you don't know the terminology, it can, as you know, can be a little confusing. Let's go on. There is an alternate form of the derivative, and it looks like this. I'm going to have you take a moment to look at it. It says the derivative of the function at c is. Now, the last thing we got the derivative was 3x squared. It wasn't a value. It was an expression. It was a function. When we use what we've been using, we are finding the derivative in general. If I want to know where it is at a certain point, I use the input of that point. What we have here, and again, some of you are writing. I hope you're listening too. Okay, but if you are writing and you're not really listening to the conversation, please go back and look at the video. Make sure you pick up the conversation here. What we're doing with this is like a one-shot wonder. Okay, this is like a one-time deal only. When we use the alternate form of the derivative, we're only finding it at a specific point. If I want to find it at another point, I got to start all over again. And that's why that general expression, that way we do it on the limit process, the other way, is a function that we can just insert the input value. I could do 10 at one, not at one time, but I could do 10 right after the other just by inserting a new value into the derivatives expression. Here, I'd have to go back and do this whole work all over again. So just want you to know, we use this, and there's times when this is more convenient to use than the limit process, but more than not, you're going to use the limit process. But let's look at this and see what we've got. It says find the derivative when the input is 6 if it exists for this function. So I only want to know what happens at this point. So let's go through, and we're going to find the derivative at 6, and that's going to be the limit. Now we have to pay attention to the difference we have in this slope, the limit of the slope here. Instead of delta x, we've got x. So we're going to say x. As x approaches what? 6, yeah. The c is equal to the 6 in this case. We have f of x minus f of 6 because we're looking at a specific point. So we're saying from the specific point, when the input is 6, what is our derivative? And then we have x minus 6. Remember, direct substitution is always the first thing we try. And if that doesn't work, we have to use all of our algebra that we know, like rationalizing the numerator or factoring out the quantities in the numerator and trying to cancel factors. And direct substitution is always the last thing we do also. The first thing we try, and it's the last thing we do. Okay, so if I try direct substitution, any problem? Absolutely. Okay, so let's continue on with our work. X approaches 6. I have f of x. I'm not going to type anything except x minus 6 to the 2/3 power minus 6 minus 6 to the 2/3 power divided by x minus 6. F of 6 is just putting 6 in for every place you see that. Limit as x approaches 6. What happens to 6 minus 6 to the 2/3 power? It's 0. Okay? So I end up with x minus 6 to the 2/3 power divided by x minus 6. Now I need a way to resolve that, a way to simplify it. Now you know that if this is to the first power, which it is, 1 can be written as a fraction in thirds as 3/3. Okay? If I have two terms of the same base, I'm going to subtract the exponents, and so my answer is going to be x minus 6 to the 1/3. What's missing? Well, how about our numerator, right? Didn't we take that quantity across the fraction line and subtract it? There's nothing more we can do algebraically. What happens with our answer here? So direct substitution leads to dividing by 0. So it does not exist. Now we need to have a reason. Okay.